So we're lucky this week to have Sampath talking to us all about what to do if our IQC is out, and hopefully there's going to be some sort of troubleshooting guidelines for us to do because we've already looked in the past about the basics of IQC. He's going to revise a few of those concepts, build on them further, and give us some cases. Thank you so much.
Thank you, Julia, and thank you all the team in Imperial for inviting me. So I start with the definition. So IQC was defined as a set of procedures for continuous assessment of laboratory work, as in WHO definition. So what we are doing is we are daily check materials using non-concentration. We expect same results in the same as we are going with the process. So it's about precision. This performance is real time, so we can deal with the issues immediately. With IQC, we can maintain the quality of the testing process and their results. These results are, we can make sure that our results are reliable and reproducible, and then it helps us to release patients' results reliably. And it also helps us to maintain our compliance with standards. But this does not give anything about accuracy, and it is not about the whole process, it is only about the analytical part. So to do that, we have something called Levy-Jennings charts, which were begun around 1930s by two pathologists. They start IQC procedure with patient samples. They measure each patient sample in a different days and check their range to monitor manual measurement processes. Later, they use single patient sample using a patient's sample pool as a one stable control. So these are called Levy-Jennings charts. And this is the typical Levy-Jennings chart. These are straightforward chart with the continuous observations of these results plotted against time or run number. X-axis contain time or day or run. Then the y-axis plotted with results. These lines are either 1 SD, 2 SD or 3 SD, which are above or below the mean. We need to have a control limit when we are defining or when we are dealing with these Levy-Jennings charts. Control limits are the lines drawn on the control chart. These are calculated. Then control rule, that means the criteria to see whether this run is in or out of control. Then this analytical run term means the individual or group of samples that we use to control. If we have a well-controlled process, as you already know, all the data appeared in a like bell-shaped curve. So 68% of all the values should fall within 1 SD, then 95.5% will be within plus or minus 2 SD, then 99.7 will be within the plus or minus 3 SD, and only 0.3% will be out of 3 SD limits. And if it is out of 3 SD, we consider them as a significant error. So this is the graphical presentation. And we have to remember that 4.5% of data will be outside of 2 SD, even with a normal analytical process. So in a Levy-Jennings chart, what we do is this same bell-shaped curve, we change the direction. So we plot them against time. So if you can see, this is our values, and here it is the time, and this will help us to identify any trends, any shift, or random errors. So in the beginning, as in first generation QC, they use single value QC with 2S control limit. But now we have multi-channel auto analyzers. We do like a lot of testing per day, and we have using a lot of controls. So because of that, if we stick into that one rule with plus or minus 2 still limit as a rejecting rule, 4.5% of all the other runs will be rejected because it has a high false rejection rate. Because of that, the Westgard introduced this Westgard multi-rule system. So these are considered as a second generation QC because we are testing, or we are using more than one test in each run. So we use 2S rule as a warning rule. Then we confirm any problem with more specific rules which have low probability of fault rejection. So the error detection is maximized by using combination of rules. These other rules are more sensitive for both random and systemic errors. So we can reject a run if any of the other rules are violated. So this is a graphical presentation. We have one is like warning rule. Then if it is there, we have to go the other rules. So before starting that, I will just go through the Westgard nomenclature. So if we go for this 1,3S rule, the number 1 is stand for the measurement involved. So if it is 1, that means it is about 1 run. 3S means that is the limit that we are using. So if it's 3S, it means 3SD. So there are two other terms like within run. That means it's a single run using two or three QC levels. When it's a across run, that means we are using a same control over few days or few time points. So this is just two other terms related to precision, repeatability and reproducibility. Repeatability usually comes with the within run precision, and the reproducibility means between run closeness of agreements. Then I'll go through Westgard rules one by one. So the first rule is 1,2S rule. This is the warning limit. This is a warning rule. This means one of our results lie outside beyond 2SD limits. This is the warning rule. If we only use one QC in our analytical process, this rule need to be accepted as a rejection rule, not as a warning rule. The next rule is 1,3S rule. This means one of our results is lie above or beyond plus or minus 3SD. So this is also a rejecting rule. This is the first rejecting rule. Then this is we have 2,2S rule. That means two of our results lie beyond 2SD. it can be either plus 2st or minus 2st from the mean, and this can interpret in within run. That means 2 levels of QC in the same day or same time point, or it can be from a cross run. That means from consecutive 2-day or 2 time point results. This is indicating a systematic error, and we have to reject the run. The next rule is R4S rule. That means 2 of our results have a difference of 4st. That means one result is beyond plus 2st, while the other one is beyond the minus 2st. This is also a rejecting rule, and also indicating a random error. The next rule is 4-1s, which means 4 of our results lie beyond 1st. This is also indicating a systematic error. We have to reject the run if we see this rule violation. Then this 10x rule means that we have 10 consecutive results beyond, we have 10 consecutive results either plus or minus side of the mean. All the results should be in one side of the Levi-Jennings chart. They are not going across the mean. So this also indicating a systematic error, and we have to reject the run if this rule is there. So there are so many rules, but all the previous rules we consider as classic rules. All the other rules we usually do not use in our day-to-day internal quality control process. So what can go wrong in our analysis? So anything can go wrong, even with our mechanical process or the analyzer electrical process or the opticals or sensors. Then again, our analytical protocol, calibration, environmental factors, water, chemical. Then again, even with the softwares, anything can go wrong, and it can generate any erroneous result. So we consider one is that there are 6 classic Westgard rules. We have one warning rule, which is 1-2s. Then we have 2 random error rules, 1-3s and R4s rule. Then we have another 3 rules which are indicating systematic errors. They are 2-2s, 1-4s and 10x. As I said earlier, all the other non-common rules we don't usually use in our day-to-day process. So then we will see what is systematic error. Systematic errors usually come with change of mean. They can either gradually changing or they can abruptly change. If it is a gradual change mean, we used to say is a trend, as in this picture. Then if it is a shift, there's a abrupt change in the mean. So there are different reasons to have a trend or shift. Trends are usually caused by deterioration of instrument light source, or they may be due to gradual accumulation of debris in the sample tubing or region tubings. They can be due to gradual accumulation of debris in the electrodes or surfaces.
Sampath, sorry, could I just interrupt? I think there's
Yeah,
one question here by Tatiana. Did you have something to ask? Oh, I think hand's gone down now. So carry on. Sorry to interrupt.
that's fine. So the trends are caused by deterioration of instrument light source, or it can be due to accumulation of debris, or they can be due to aging of regions, or probably aging of control materials. There can be gradual deterioration of incubation chambers, or they may be something related to filters or calibrations. So everything is like changing gradually throughout time. That is why there's a trend. Shift are usually caused by sudden changes. So there can be sudden failure of light source or the filters or detectors, or then there can be sudden change in region formulation or region load. They can be seen after major instrument maintenance. They can be either seen after incubation temperature. This is usually happen with enzyme assays, or if the reaction or the analytical process involves enzymes. Then even if we have a change in room temperature or humidity, they can also give us these problems. Then if we have a failure in our analytical process, like in sample tubes or vacuum, again, we can see these results as a shift in our QC process. Even if there's something wrong with the region dispensing system or calibrator, then again we can see shift. If you use inaccurate calibrators, or if you do recalibration, again it can cause a shift. So what are random errors? Random errors are any positive or negative deviations. So if you see a random error, we have to see whether this is within the acceptable limit, or if it is considered as an acceptable random error, as in 1 to S rule, when we consider as a warning rule. So these acceptable errors we need to define before implementing the QC process. What are the causes? They can be usually caused by incorrect samples. Then these are usually caused by air bubbles in regions or even region lines. Then if it is inadequate mix regions, again, same thing happens. Sometimes there can be damaged quartz or damaged quartz in the system that we have used for do the QC procedure. So again, it can cause random error. So what we do if we see one of these rejecting rule. So the first thing is to repeat with the test with the fresh QC. So what is the important thing in repeating QC is, when we are repeating the thing, if we have something like we have using expired QC, or if sometimes by mistake we can use a wrong QC level. So when we are repeating something, the person who is doing the test usually give more attention to these random human errors. So it will help to identify if that is there. So if the repeat results come as normal, we can just review the trends and all the other QC findings in the Levi-Jennings chart. We can go ahead with the patient results and release the patient results. If the repeat results is abnormal, we should not repeat again. We have to stop measuring samples. Then we have to calibrate, or we may have to replace regions, and then do the QC again. If it is fixed, then we can process with the samples, or we can release the results. If you do any changes to our system, we have to rerun all the controls before releasing the result. If after doing the repeat calibration and all the things, if it is fail, then we have to call the manufacturer and get their engineer support. We have to identify all the samples that were run after last normal QC, and we may need to repeat all these patient samples on another analyzer. So when we are finding out possible etiologies, we have to look for the clinical input. We have to, so when we are responding to out of control event, we have to give a clinical input. We have to assess the impact of the changes into patient management. Sometimes we may only need to replace results if there's a management impact. If there's an urgent results, we may need to call the results. Then we have to see whether this condition is going to be persist or transient. If it is a persistent condition, we may have to go through intermediate and long-term management plan. Then we need to have preventive measures like documentation of all the errors, and then if we have a QC log, it will be helpful to prevent all these problems. In a QC log, we should document the QC material preparation, QC results inspection, and the things that we observe in the Levi-Jennings chart. So how do you identify the etiologies of all these problems? To do that, we may have to go to Westgard rules and check whether these are coming from a systematic or random error. So to do that, we have to check the patterns of the QC results. We have to check whether there's any commonality between our failed QCs. Sometimes all the wrong or out of control results come from a certain photometric assays. Probably all of them may be electrolyzed results, or sometimes they all may use some common reaction like NAD/NADH reaction, or sometimes they may all have a commonality like a redox reaction. So sometimes they may use same module, same wash system, or something like that. Then we have to see, is there any change that we did after the last good IQC results? It may be related to calibration, region changes, or new lab, or something like that. Or we may have used a new kit after the previous IQC. Or we may have has done a new calibration. Sometimes we may encounter with these errors, and they are all the out of control has come from a single control. So we have to look at our controls and see whether we are using a multiple test QC. And it is also important to see how far from these results from the mean. Usually if it is very far from the mean, it will be something very uncommon. So we have to check previous Levi-Jennings chart and look for a trend if we are looking for a cause. So to identifying a cause, we should have a good knowledge of our analyzer as well as our IQC data, and we should have a way of detecting potential problems. Then we should have IQC review, and even with the IQC receive, we can it will tell us about our IQC materials, because if the material is changing, it will show in our Levi-Jennings charts. When we are implementing our targets, we should have realistic targets, because otherwise we will have a lot of false alarms. And we also should know the stability of our assays before determining the IQC frequency. And we have to know about our QC materials as well. QC materials are usually the specimens that are analyzed for QC purposes. So they have different stability, they have different expiry date, and there are wild variations, and also some of them need preparations. So there are two QC materials. One is liquid QC samples, and liquid QC samples have usually have other materials that can cause errors in some analytical methods. If we are using reconstituted QC samples, their stability can be an issue for certain analytes, and they can also introduce errors when we are making these samples. So Westgard rules usually comes with the second generation QCs. Now we are in an era of third or fourth generation QC, which is focused on total quality management, and they help us to design our QC procedure. Total quality management means it involves all the processes and performance involving our laboratory test process. So it means that test is always focused with their intended use and the test method. So when we are designing QC procedure, we have to think about the test fit for its performance. So its performance characteristic and the analytical system performance and also the technology is important. As now we have very advanced technology, these days QCs need very less frequent controls. So it can improve our throughput by decreasing fault rejection rates. By optimizing QC design, it will help us to do a cost-effective quality control. So laboratory quality of a clinical laboratory test depends on the purpose. The purposes are like test. We can use a test for diagnostic purpose or screening purpose or monitoring purpose. So effect of the analytical performance on a test depend on the clinical decision that we are going to make. So these there are various recommendations from professionals about these quality of these clinical laboratory tests, and we can use these recommendation to set our quality specification in our QC program. These quality specification may come from regulators or from external or IQC organizers, or come from a published data, or they can be based on biological variations. When we are planning a QC, we have to consider all these factors. Some of these factors like biological variation goals or diagnostic classification may impact the performance criteria of a QC program, and then some of these clinical factors like medically important changes affect on the clinical outcome of the test, and the others like proficiency testing or the biological goals address the analytical outcome of a test. So everything is going to be end up in a affect the whole operating system and operating specification. So if we are going to design our IQC program, the general guidelines is like, first we have to define the current requirement, then determine our method precision and bias, then we have to identify a candidate IQC procedures, then we have to predict our IQC performance, then we can set our goals for our IQC performance, then we can select an appropriate IQC procedure. There are a lot of guidelines and frameworks available to do this. Then we have a thing called Six Sigma, which comes with the 5th generation QC. So this Six Sigma is something about a tolerance limit based on intended use to set a goal. So the Six Sigma process described in terms of defects. So it can be defects per million, defects per thousand, like that. There's a Sigma scale which spread from 6 to 1. 6 is considered as a best case, while 3 or low considered as worst case. If we have a sigma less than 3, it is not acceptable. So this Six Sigma provide a quantitative framework for process performance. Then it gives us a objective evidence for improvement of our test procedure. Then we can assess our process to compare with another system, or even we can compare our two of our assays with this Six Sigma process. So Sigma is something like this. It shows where we stand with allowable tolerance or allowable range. I'll give you one example how we are doing this. If we have two systems and if we know the assay's total allowable error, we can calculate our sigma. We need to know our bias and our CV, then we can calculate sigma using this formula. And for the system X, our sigma is 4. And for the system Y, our sigma is 2.5. So we know that 4 is better than 2.5. So we can easily compare these two systems, and we know that system X is performing better compared to system Y. What is the importance of this? So if we have a sigma score of 6 or more, we need to do our IQC system, we can use a less frequent IQC. We can just do one QC or one quality control per day. Then we can reduce the number of levels that we are going to use. And also we can stick to a 1 or 2 QC rules. If we have low sigma score, that means we have to use high frequent QCs, and we have to use more levels of QCs, and we have to use multiple rules in our IQC program. So this is the same thing. So this is what I said earlier. So let's say if we have a sigma as a 6 sigma, then we can only use one rule like 1,3S and 2 controls and only one rule. And our QC frequency is like 1 in 1,000 samples. If you have a sigma like 5 sigma, then we have to use 2 rules, and we have to do QCs after each 450 patient samples. If we have very low sigma like 3 sigma, we have to use 6 rules, and we have to run QC after like 45 patient samples. So I'll give you one example of how this sigma rule was used to improve analytical process. This is from a paper. They have described this on their CSF sample testing. For CSF albumin, they have a sigma of 8.8 and 8.6, and then total protein, it's again above 6. CSF chloride, again above 6, and CSF glucose, it is less than 6. So if you see this chart, CSF glucose has a sigma of 5, where it says excellent, but all the others had the world-class sigma of 6 or high. So what is the problem, or what is the impact of this sigma value? So as all the albumin, troponin, and chloride has high sigmas, they are using only one QC rule and 2 controls, and they are doing QCs in 1 in thousands. But for glucose, they have used all these 3 rules with 2 controls, and they are using QCs in each 440 samples. Then what they have done is they have analyzed to improve the performance. They have analyzed their system to see what's wrong with the glucose. So they have noticed that their performance is poor because of imprecision. So throughout next 6 months, they have tried to improve their imprecision by addressing these issues. They have changed personal factors, like they have done the staff training and assessment. Then they have improved their instruments by instrument maintenance and everything. Then they have changed the materials, region selection and evaluation was done for monitoring lot to lot variations and all the other things. Then they have selected a method, and then they have even done the environmental factors like temperature and humidity monitoring. After 6 months, they have been achieved this sigma value of 6.3 and 6.5, and they have moved from excellent level sigma to a world-class level of 6 sigma, more than 6. That is all for my IQC and Westgard rules. Then I have some clinical scenarios. Shall I straight away move to that?
Yeah, I think so. Unless anybody's got any particular questions, then that'd be great.
Okay. So the first question is, or the first scenario is, if we have given a new control material which is supplied with the mean and a reagent of 2ST from the manufacturer, what is the proper use of the mean and range? I'll give few minutes to think about it. I mean, few seconds. So what we have to do is, first we have to confirm that our laboratory mean is within the given 2ST range supplied by the manufacturer. But then we have to use our own our laboratory mean and QCs. Because if we use manufacturer's QC, manufacturer's mean and ST, sometimes we may have falls within our acceptable range. The next question is, how do we calculate our control limits? So it is the calculating ST and mean, but we have to use our own laboratory mean and ST, not the manufacturer's mean or manufacturer's data. So it is the same thing again. our own mean and standard deviation will help us to have a narrow control limits. If you use manufacturer's SD that came from a large group of labs, it will widen our limits and it will miss in some errors. The next question was when the warning rule 2S is violated, what actions do we need to take? If we are running 3 controls, upper sorry, that's a 3 question. First question is when the warning rule 1-2S is violated, what action do you take? Second question is running 3 controls, upper, normal and lower level control. When one control material is beyond 2SD control limits, what is the first response in this scenario? Third question is the upper control value is above 1SD, while the lower control value is below 1SD. What is the first response in this scenario? So all these scenarios, we only need to check whether we have violated any other West Guard rules because everything is just above and beyond 2SD. So all these are like warning rules. So the next question is, given a cholesterol test where the low control has mean of 190 and SD of 3, and high control material has a mean of 250 and SD of 4, when the control values are 197 and 243, what will you do? So for this scenario, for higher level control, plus 2SD is 258 and the minus 2SD is 242. So our value 423, 243, just beyond 2SD, while the 197 is sorry, 100, this low QC is above plus 2SD, while the high QC within the 1 to 2SDs. So it's only 1 QC out of 2SD. So we don't have to do anything. We just have to accept the run because it is 1-2S rule. The next one is, if we are running 2 controls, upper level and a lower control level, when both control materials are out beyond 2SD control limits, what is the first response in this scenario? So we have to reject the run and do the troubleshoot because we have 2S rule violation. When both control materials are below their respective means and the values for the previous 4 runs were also below the mean, what is the first response in this scenario? So that means we have 8 results, previous 8 results below the mean, and now we have 2 results below means. So this will give 10x rule and we have to reject the run. What will you do in this scenario? So here, there's something happening after these points. So it depends on what we did at these points. So they can be due to gradual deterioration of calibration, because deterioration of light source will not happen frequently. So gradual deterioration of calibration, gradual accumulation of debris, or accumulation of debris on the surface, or aging regions, or anything can happen. So the cause will depend on the what we have done at this point. If we have done the calibration change, it will be something related to calibrators. If we do a maintenance or something, then there's something wrong with this, like accumulation of debris or something related to our system. Even sunlight, exposure to some sunlight can cause this kind of errors. I think that's all for me, and thank you for listening.